Okay, so we're gonna do this here review, and let's see, I need a few writing utensils at my disposal, and maybe a pen or two, periodic table, calculator, got it, check, check, check. All right, so J.J. Thompson, the elder statesman, he gave us the plum pudding model, aka the chocolate chip cookie model. I'm going to bleed over a little bit there, but that's going to have to do. And the merits, what he gave us was the electron, basically. The electron, the charge. He gave us the charge to mass ratio. It doesn't have much mass, but and it's very small, but it does have some charge. Electrons are, they're negative. They're negatively charged. That's what he gave us, and he basically said it was on a background of positive, like he didn't have any idea. So the limitations, the negatives of his particular model is he had no idea about the nucleus or anything that was in the nucleus. Like he had an idea that there was a positive background noise, but he didn't know what it was. So no protons, no neutrons, no anything that was in the nucleus. So basically, that was Thomson. He gave us the electron, charge to mass ratio. And then Rutherford comes along, and he does his gold foil experiment. And basically, he takes some gold foil, shoots some alpha particles through it, and all an alpha particle is a proton. It's a positively charged particle, a proton all by itself, maybe with one neutron attached. But you can get atoms to degrade and shoot off these alpha particles anyway. And he did that, and he shot over and over and over and over and over through this thin gold foil, and most of the time he hit nothing. Some of the time he deflected, so he knew there was a positive charge in the middle of the atom. And some of the times it reflected straight back, but only very rarely. I think it was like 1 in 294,000. They had a continuing experiment, but I can't find it anymore. So you'll just have to look up Rutherford experiment and see how many times he had to shoot to get one to come back at him. But what he gave us was a dense, positively charged nucleus. And he figured out that the atom is mostly empty space. Mostly empty. So the limitations of his model were basically all he kind of figured out were the protons were there. He kind of figured out the structure of it. But he didn't tell us anything about electrons. No electrons. So we still didn't know where they lived. Oh, no. See, this is why I put two of them up here. No electrons. And basically, we didn't get neutrons until I think it was Dalton came along and gave us neutrons. So we won't ever know about neutrons in any of these models. But he didn't know about electrons or where electrons lived. Okay, so then along comes Bohr, and he gives us this planetary model. And basically what he says is that, why is it so dark? Why is the camera so dark all of a sudden? It's almost like it went really dark all of a sudden. What's going on here? Okay, well, I apologize for a camera. I've never gotten a workable camera, document camera, in this room. I don't know what it is. I've tried 3 of them. Anyway, hopefully you'll see where I'm pointing and hear what I'm saying. Anyway, planetary model. So that's that nucleus and the electrons traveling around. If you've ever seen Big Bang Theory, you've seen the electrons traveling around in these spheres. Bohr gave us that, and they gave us shells. So electrons would be like the different planetary orbits around a planet. or around a sun, and that sun is our nucleus. And so basically the electron shells become these orbits, and so he gave us shells of electrons. Gave us shells of electrons, and he also gave us a very particular thing that happens in hydrogen. So hydrogen only has one electron, and it has a nucleus there. And if I excite that hydrogen with, say, with electricity, I can do it with one of these little these gadgets I have to show this. But anyway, I can excite this electron from its ground state to its excited state, which is a second shell, right? It goes up a level in energy, and once it's there, it'll move away from whatever energy source that it's receiving energy, and so it will start to drop back down, but it will have to give off energy, and it gives off that energy as a photon of light. So the electron goes from ground state to excited state because it picks up energy from some external source, and then when it wants to drop back down, it has to get rid of that energy, and so it gets rid of it as a photon as it drops back down. Make sure you understand that it's as it drops back down. That is called the Bohr model of light emission. And I'm going to go ahead and tell you right now, the limitation of this is he only did hydrogen. That's the only atom he did. You did more doing the flame test to show that other electrons can jump shells than he did. All he did was with hydrogen, so he was limited to hydrogen, and he didn't really tell us exactly where electrons lived. No exact address for electrons. That came with Schrodinger in the current model. We call this the cloud of electrons. Cloud of electrons model. It's based on probability. It's based on math. Everything is at its core based on probability. And there are no limitations. If there was a limitation, if we knew it had a limitation, we would make a new model. That's the way models work. You make a model, and then somebody comes along and they improve upon it, and then you know that you had a limitation. We didn't know that Thomson had any limitations until Rutherford and these other guys came along. All right, called the planetary model, that's Bohr. C. First model to have a nucleus, that's Rutherford. B. Referred to as the electron cloud model, that is the current Erwin Schrodinger model. First model to say that electrons could only exist in specific energy levels, that's why it's the planetary model, Bohr. Called the plum pudding model, Thomson, first guy, J.J., Thomson, no P. First model to have electrons but no nucleus, also Thomson. What's going on up there? Model could only really explain hydrogen's behavior. Well, that's Bohr again. I mean, you'd have to kind of understand that we're talking about light emission there. Could not explain the arrangement of electrons outside of the nucleus. Well, that's Thomson and Rutherford. Neither one of them had a clue about electrons arrangement outside of the nucleus. So Rutherford was concentrated mostly on the nucleus, and Thomson really didn't know where the electrons lived. He just knew that their charge to mass ratio was something that you could look up. Okay, page 2. All right, proton symbol P plus. Electron, E minus. Neutron, N naught. Charge, plus. Electron, minus. Neutron, no charge. And you could say minus 1, plus 1. It helps you kind of navigate the oxidation numbers and charges of things later. So it's okay to say plus 1, minus 1. Relative mass, 1 AMU. What's beeping at me? Electron. No relative mass, because it's an electron, neutron, 1 AMU. They weigh the same as protons. Location in atom, nucleus. Protons are in the nucleus. Okay, electrons are in clouds around nucleus. And the neutron is in the nucleus. All right, determines or affects. This is an interesting one that y'all sometimes have trouble with. The proton determines the element. If I have one proton, it's a hydrogen, full stop. If I have two protons, it's a helium. So that determines the element. Electron determines the ion. It determines if it is a cation or an anion. So the number of electrons determines the ion, and neutrons determine the isotope. Basically, a different number of isotopes means a different number of this beeping is driving me crazy. Different number of neutrons means a different isotope. So I can have carbon 12, I can have carbon 13. Carbon 12 has 6 neutrons. Carbon 13 has 7 neutrons. All right. Define atomic number and mass number. Oh my God, you are killing me. The atomic number is equal to the number of protons, and in a neutral atom, the number of electrons, but I don't want to get hung up on that. In a neutral atom, protons are equal to electrons. That's all that matters to us. And mass number is equal to protons plus neutrons. So, if I have protons and I have mass number, then I know number of neutrons. Or if I have a mass number and I have number of neutrons, then I have number of protons. It all comes out in the wash, right? What do they tell us about isotopes? Well, the number of neutrons tells us the number of protons and neutrons tells us the mass number. So that gives us the isotope number. So when I say carbon 12, the 12 is the mass number. Carbon has an atomic number of 6, so it has 6 protons. What is an ion? An ion is an atom. Cheap pencils. Atom that has a differing number. That means two different numbers. Differing. Oh my gosh. I'm not an English teacher, guys. Differing. No, that doesn't look right either. Differing number of protons and electrons. And it says, explain how they are formed and state the difference between cations and anions. No problem. They are formed by losing or gaining electrons. Cations, cats are positive. See, I'll draw a cat paw and a little positive symbol, and you'll say cats are positive. And anions are negative, so cations are positive. I'm getting my other pencil back. Where is my other pencil? There it is. So this one's hot garbage. Cations are positive, and anions are negative. Cats are positive. You'll always remember that. Identify the parts of this isotopic notation, also called nuclear notation. How many protons, neutrons, and electrons are in this element? Well, protons are easy. This is called the atomic number here, which is also the number of protons. So that's convenient. This is the mass number, which is also the protons plus neutrons. So if I need to know the number of neutrons, all I have to do is subtract the bottom number from the top number. 23 minus 11 is 12. This thing has 12 neutrons. It has 11 protons, and it has a +1 charge. So what I always say is do the opposite of this with your electrons. So you need to subtract 1 electron. If you see a positive here, subtract 1 electron. If you see a negative here, you need to add electrons. So this is going to have 1 less electron than it has protons, so it's going to have 10 electrons. That's where I get that positive charge. I've got 1 extra proton that is positively charged. That is the oxidation number. Oxidation number. And that just tells us what atoms like to do. We know that things in group 1 have one valence electron. They like to lose one electron. Things in group 2 have two valence electrons. They like to lose 2 electrons, and so on, until you get to 5 electrons, and then we like to gain 3 electrons. Does that make sense? Gosh, I hope so. Okay. Man, I hate this camera. This camera is garbage. I can barely see anything. If I draw this down a little bit, does it get clearer? No. Why do you not? Why? Okay, well that's actually better up there. I don't know why. Sorry about this, guys. If you know of a better document camera in this school and somebody who's willing to loan it out, I need something desperately. Anyway. Okay, so here we have argon, and it says its atomic number is 18 and its mass number is 40, and they want the isotopic symbol. If they had asked for the name, I would say it's argon 40, but they want the symbol. So the symbol is the atomic symbol or the elemental symbol for argon, which is Ar. You can see that right there on the periodic table. The number of protons, well, the atomic number is the number of protons. The number of neutrons, and so I need to finish up this isotopic symbol. The number of neutrons can be gotten from the mass number. If I subtract 18 from 40, I get 22 neutrons. And then the number of electrons, we're assuming all of these are neutral atoms because nothing is here to tell me otherwise, that these are not neutral atoms. So I'm going to say this thing has 18 electrons just like it has 18 protons. So atomic number, protons, and electrons are all the same in a neutral atom. Bromine, so Br, and now I'm going to do the whole isotopic, so it's 35 on bottom and 80 up top. And 35 from 80 is what, 45? 45 neutrons. I have 35 protons. I have 35 electrons. And that's bromine, and it's no charge bromine. Then I have uranium, so U, and the atomic number on bottom, 92, and the mass number on top, 238. And I'm not even going to try and do that in my head right now. 238 minus 92 is 146 neutrons. So the 92 goes in here for protons and right in here for electrons, and that is one chart down. So hopefully isotopic symbols aren't a big problem. We always assume an atom is neutral unless they give us some indication that it's not, like this plus symbol on the sodium here. Okay, I'm going to cut this video off at probably 30 minutes because it takes them so long to process something that's 30 minutes. It's actually easier for me to dump a bunch of 30-minute videos on there if I have to. Okay, isotope. Well, they give me a mass number and they give me a number of protons. And if you give me a number of protons, then I can tell you what it is because that's the atomic number. The number of protons is the atomic number. So this is fluorine. This is fluorine. And they want the isotope, so I have to put the mass number at the end. This is the isotope name. It doesn't say that, but I see uranium-235, and that's how we do naming of isotopes. It's basically, I can't. Can you even? No, you can't even see any of that at all. Can you see my writing? No. Perhaps at about a distance right there. I don't know. Anyway, it's fluorine-19. Its atomic number is 9 because it's going to have the same number of protons and it's going to have the same number of electrons if it doesn't have a charge on it, but it has a charge of -1. Well, first let's figure out these neutrons. The mass number minus the number of protons is the number of neutrons. 19 minus 9 is 10 neutrons. And now you do the opposite of what it says. So I'm going to add 1 electron. So this thing has 9 protons, 9 electrons. I'm going to add an electron and give it 10 electrons. And by the way, you can look at the noble gas group, and any time you make an ion, it's going to have 2, 10, 18, 36, 54, or 86 electrons. That's all it will ever have if it is an ion. And I will prove that down here with this +2 ion down here. It will end up as something that is 10, 18, 36, 54, or 86, guaranteed. Okay. So the second one has no charge, and it has 90 electrons, so they basically gone backwards and given us the number of protons, which gives us the atomic number, which gives us that this is atomic number 90. What is that? Where is that? Where is that? That's way down here. This is thorium, TH. So thorium, and do I have a mass number yet? No, I have a number of neutrons. So protons plus neutrons equals mass number. This is going to be 233 is my mass number. So this is thorium 233. And that part of the chart is done. Next I have uranium 235. And its atomic number, if I look, uranium, it's right here. It's atomic number 92. And I don't know its mass number. So we're going to talk about that in a second. Well, I do know its mass number from its name, but we're going to talk about that in just a second. You might have to look at the name for the mass number because there's no way for, and there's no other place for you to look. If they don't give you neutrons and they don't give you, or they don't give you protons and neutrons, they have to give you the mass number. So here they've given it to me. It's 235, ooh. And I have 92 protons, and if I take 235 minus 92, oh, again, math, 235 minus 92 is 143. 143 neutrons. Same number of neutrons, cool. This thing doesn't have a charge. It's got 92 protons, so it's got 92 electrons as well. It has 0 charge. That's awesome. All right, last and least. I mean, not least. 56. So he is barium. This is barium. Barium dash. And do we have a mass number? No, but we have a number of neutrons. So the number of neutrons plus the number of protons, which is 56. 56 plus 80 is what? 136. 136 is our mass number. This is barium 136. And the number of electrons. Now, here we go. It has 56. I'm going to subtract 2 electrons. That's going to give me 54 electrons. Guess what I said? I said it's going to have 10, 18, 36, 54, or 86. And it has 54 electrons. Everything loses or gains electrons to be like a noble gas. And xenon here has 54 electrons in it. And the fluorine is -1, so it has 10 electrons. And it's like neon. Neon has 10 electrons. So 10 or 18 or 36 or 54, which is what this one came out to be, or 86, those are pretty much where all the ions land. Okay. Yeah, I'm not supposed to do the on your own part, but since it's just my class, y'all don't tell nobody. I don't believe in y'all not having answers to the review, so let's just go ahead and do this part, and I'll trust that you know how to do this because you're just doing the same thing that I did above this. So that one I won't do. This one I will do. What I have is strontium, and it says explain how you'd find the number of protons, neutrons, and electrons. Well, this is a neutral atom, so it has 38 protons. How do I know that? Because the atomic number is on bottom. And that is the number of protons. And the mass number is on top, so that's protons plus neutrons. So 90 minus 38 is equal to 52. So this thing has 52 neutrons. And it has no charge. We said earlier it has no charge, so it has 38 electrons, has the same number of protons and electrons, so zeroes out the charge. And that's it. 38 protons, 52 neutrons, 38 electrons. Then we got this phosphorus over here, and so we're going to have to add some electrons because I see the minus symbol. We're going to have to add 3 electrons, and guess how many it's going to have? Well, you'll figure it out in a second. So here we have phosphorus, and it has 15 protons. And then I can subtract this from the mass number and get 17 neutrons. 32 minus 15 is 17, so I got neutrons. But it has a charge, so I don't have 15 electrons. I have to add 3 electrons to get 18 electrons. Hey, just like argon. Argon has 18 electrons. 18 electrons. So I had to add 3 to get that minus 3 charge. So I do the opposite of what the charge says, and I add 3 electrons. Or if it's positive, then I subtract electrons. Okay, yeah, these are the two tables that I just did, and I'm not going to do the same table over again. I will do this down here and this down here. All right. Yes, we do use the atomic number to identify an element, and not, why do we use the atomic number to identify an element and not the other subatomic particles? Well, because neutrons, I just proved it. We have two things with the same number of neutrons. It would hardly do to identify thorium and uranium as exactly the same because they have the same number of neutrons. The only thing, and I already told you that things have the same number of electrons as noble gases. That's why they lose and gain. So lots of things have the same number of electrons. The only thing that actually identifies an element is the number of protons, because that doesn't change, it doesn't vary, it doesn't waver. You can't remove them unless you have an atom smasher and unless you're going to do some fission. If you're going to do some fission, then you're going to smash some atoms apart, and you might be able to change the number of protons. Okay, Peter, Paul, and Mary, great band, are having an argument over the newest element added to the periodic table. Peter and Paul say that elements X and Y are isotopes. Well, what is an isotope? An isotope is the same element that has a different number of neutrons. Well, these have 120 protons and 122 protons, so I'm going to say Peter and Paul are dumb. No, they're not dumb. They just don't know anything about chemistry, and they made a wild assumption about these two elements. I'm not sure why. Probably because they're singers in a band. Mary says that the elements X and Z are isotopes. X and Z have the same number of protons, 120, and different numbers of neutrons, 140 and 141. So whatever this element is, it's X261 and X260. So that's going to be the two isotopes of that. Mary is correct. Yeah, Mary's so smart. She's going to be a great chemist one day. What is average atomic mass? That's that number on the bottom of the periodic table. That's that guy. That's the average atomic mass for carbon. It's 12.01. It's a weighted average. Is it the same thing as atomic mass? Yes, it is. Average atomic mass, weighted atomic mass, we call this all the same thing. The only thing that's different is mass number. Mass number is protons plus neutrons. Okay, protons plus neutrons. So mass number is one isotope. When we talk about average atomic mass and atomic mass, the thing on the periodic table, that is the weighted average of all the isotopes of whatever it is we're talking about. So that's why the man-made stuff only has one number, because we don't man-make different types of isotopes. We make one isotope. And so it has one number that looks like a mass number, because it is. Like, we put together a certain amount of protons and neutrons, and we make some new elements. Okay, where are we at? We're at 28 minutes. All right, I'm going to cut this video off, and then I'm going to continue, and I think the next video we can probably get this done. All right, so we're going to have two 20-plus minute videos, but it'll be all right.